Hi class, in this video here we want to begin in section 3.1 talking about exponential functions. And so you probably have in your previous math classes learned what an exponential function is. So I'm going to go really quickly through it, talk about the graph, do one graph, and then I'll get into the calculus of exponential functions. So an exponential function f is given by this. So it's f of x is equal to a to the x, okay? This x here, this can be any real number. Okay, so that's the input of the function is the exponent. And a here is called the base. Okay, so it's the base of the exponential function. The restrictions on a is a has to be greater than or equal to 0, and a just can't equal 1. Because then you'd have 1 raised to any power, and it would just be 1. So we say that a is not equal to 1. And so here are some examples of exponential functions. 2 to the x, 1/2 to the x power, 0.4 to the x power. These are all exponential functions, okay? Anything. F of x is equal 5 to the x power. F of x is equal to 1/3 to the x power. Anything like that is considered an exponential function. So what did the graph of an exponential function look like? So if f of x is equal to a sub 0, so this is just a coefficient here, okay? Times a of x. If a is greater than 1, okay, this graph is positive, increasing, and continuous function as x gets smaller. And then as x gets smaller, negative, like -1, -2, -3, so on and so on, this approaches 0. So what will happen is the graph will have a horizontal asymptote at the x-axis for negative values. And then as x gets larger, positive, the graph goes, whoop, shoots up like this. And I'm going to do two examples so you'll see. The flip side here, if a is between 0 and 1, so something like, let me just go back for a second. Something like this would be something like this, 2 to the x. Okay, the graph would look something like this. All right, if now all of a sudden if a is between 0 and 1, so it's like a fraction, it's positive decreasing continuous function. Okay, so as x gets larger, this graph, as x increases, it approaches 0, so it has this horizontal asymptote at the x-axis here, and it's just the flip side of it. So in this case, when x is negative values, the graph goes whoop, shoots up. Let me show you the graph very, very easily of two exponential functions. So I'll show you the graph of 2x, something like this, and then I'll show you another one, say f of x is 1/2 to the x power. All right, so here's what the graph of f of x equal to 2x looks like. So the first thing you're going to do is you're going to find some function values. So what you're going to do is you're going to pick test values for x, and what you're going to do is you're going to plug it into the function. Okay, and when you do, you'd get all these different test points. So the point 0, 1, 1, 2, right here, 2, 4, you can see 3, 8. Like when I plug 3 into this, it becomes 2 to the 3rd power, which is 8. And so on. Like when you plug in -1, you get 1/2, and so on. And you can use these test points to show what the graph of this function would look like. Okay, so I'm going to leave this in the notes here, and you can look over this in more detail. But let me do an example for you here, just straight up, that you might not have done before. So f of x is equal to 1/2 to the x power. So what does the graph of this exponential function look like? Well, look, here, this value, my a, is 1/2, my base of the function. So if you look back, when we sketch this graph, it really, really should look like this. Okay, so let's verify that. So we're going to pick x values to create a table, and we're going to plug them in. So here are the values. I'm going to pick -2, -1, 0, 1, and 2. Sorry, to the x power. Okay, so f of x is equal to 1/2 to the -2. Well, negative exponent, right? What you would do to turn this positive is you would flip this fraction. So this would be 2 squared, which is 4. So my first test point is -2, 4. Same thing with -1. So my next test point would be -1, 2. And you can see how this is looking. So I plugged in -2, -1. Now I plug in 0. Anything to the 0 power is 1, so you get 0, 1. And then look, f of 1, you get 1/2 to the first power, which is 1/2. So you get the point 1, 1/2. And then you can see it's just going to very, very quickly shoot down towards the asymptote of the x-axis. So you get the next point 2, 1/4. And you can see this graph. If you plugged in -3, you get 8. So this graph, this graph really does look, my stylist here is not the greatest at showing this, but you can see what this graph looks like here. And it does match, just by looking at these test points, it absolutely does match what we thought it would look like here. Okay, so what we're going to actually spend most of our time on in this section here is the natural base. Okay, so we call the number e, I always find that funny, right? The number e, because it's a letter. We call the number e the natural base. And what e is equal to, it's equal to the limit as h goes to 0 of 1 plus h raised to the 1 over h power. And it's just equal to this number. Okay, it's an irrational number, so it keeps going. It's just equal to 2.71. And hopefully you've seen e before, especially in your pre-calculus classes. So what we want to now focus on is the derivative of e. So the derivative of a function f given by f of x is equal to e to the x. Okay, so this is our function, is itself. So it turns out that the derivative of e to the x, so if you just look at this notation here, derivative with respect to x of e to the x is just e to the x. Okay, that's actually one of the easiest derivatives we would have in this course. Okay, so let's just do some examples, and I'll put this up here. So just recall the derivative with respect to x of e to the x is just equal to e to the x. So I want to find dy dx for these. So I'm going to take the derivative here. Dy dx is equal to, well, 3, that's just a coefficient, so that just stays. And then the derivative of e to the x is just e to the x. So that's pretty easy right here. Here, you're going to need to use the product rule. So dy dx here. Take the derivative of x squared, you get 2x times e to the x plus x squared, and then the derivative of e to the x is just e to the x. And then over here, you would need the quotient rule because it's a division. So dy dx here is equal to derivative of the numerator, which is e to the x, times x cubed, so I'm going to put that in front, minus the derivative of the denominator, which would be 3x squared, times the derivative of the numerator. Well, the derivative of e to the x is just e to the x, all over the denominator squared. So here you can just see how you're going to factor out an x squared. And this becomes x to the 6th, and you see the squared will cancel with this, and you're just left with x e to the x minus 3 e to the x over x to the 4th power. So just this is just the important thing. All the rules of derivatives apply here. You're just very easily, whenever you see the exponential function e to the x, the derivative of e to the x is just e to the x. All right, let's talk about this now in terms of the chain rule. Okay, so the derivative of e to some power is the product of e, all right, to that power and the derivative of that power. So it's really just the chain rule. Okay, so the derivative with respect to x of e raised to the f of x. So f of x is some function of x. You just take e to the f of x times the derivative of whatever that function is. Or derivative with respect to x of e to the u is equal to e to the u times du dx. All right, let me just show you with a very simple example. Consider e to the 2x here. Well, this is my f of x. So the derivative with respect to x of e to the 2x. You just write it as e to the 2x times the derivative of whatever the exponent is. So times the derivative of 2x is just 2. So this is just 2e to the 2x. So, just rewrite it and then multiply by the derivative of the exponent. All right, let's do 3 quick examples here. Pretty straightforward. Okay, so let's differentiate each of the following with respect to x. So here, dy dx. So I'm going to do this a little bit differently. So first thing I'm going to do is I'm going to look at the exponent. Okay, what is the derivative of the exponent? The derivative of 8x is 8, and then you're just going to rewrite this as e raised to the 8x. So take the derivative of the exponent and then multiply by e by itself again. And that's it. That's all you have to do. So here, dy dx. We're going to take the derivative of the exponent, okay? Well, the derivative, just go piece by piece. This becomes minus, the derivative of minus x squared is minus 2x. The derivative of 4x is plus 4. And now I'm going to go e and then just rewrite whatever the exponent is. All right, here, I'm going to rewrite this just so it helps a little. Y is equal to e and then x squared minus 3 to the 1/2 power. All right, so this one's a little bit trickier because when you go to take the derivative of this, you're going to have to chain rule. So this is like a chain rule problem. Okay, so start by taking the derivative of this. Okay, so bring the 1/2 down. X squared minus 3 to the minus 1/2. But then you have to take the derivative of the inside still. So the derivative of x squared becomes 2x. And then the derivative of minus 3 is 0, so that just goes away. Times, and then just e, and then you just rewrite this. So now you literally have to clean this up, right? So the 2's cancel. Bring the negative exponent down. So this is e to the x squared minus 3 to the 1/2 power divided by x squared minus 3 to the 1/2 power. So you can even rewrite this as e to the square root of x squared minus 3 all over the square root of x squared minus 3. So that one you just had to use the chain rule twice there to figure it out. But again, what I'm hitting home here is just take the derivative of the exponent and then multiply it by the original expression. And that's it every time.